Good evening. Sort of head spinning to hear all the comments and find that they refer to me. The leadership of getting a bipartisan support of anything, if it's just me, that's encouraging. So thank you very much. And it's a wonderful evening for me, particularly in fact because of a lot of you who are here who show an interest not only in the capabilities but the potential of the Research Institute as it's now roughly 9 years old, as John Murphy referred to it as the end of the beginning, which I think is a great reference to where we are. Justice Scalia, I happen to have spent a little bit of time, and he tells about the first time that he was asked to give a graduation address at a prestigious law school, and he hadn't done that before. So we went around, he knew a couple of other justices did, and so we went around and asked them what he should talk about. And he said the opinion was unanimous, he should talk about 15 minutes. Which so I'll go with the justice's comment. Grace visibly blanched when she asked what the topic of my talk was going to be, and I said, think small. That's not what the Director of Development wants to have as their next campaign slogan, but that's it indeed. You know, the way papers start or books start with a couple of quotes to sort of set off the general theme. And the first one would be Protagoras said to Plato 660 BC roughly, "The man is the measure of all things." Then the next quote is from the movie Alive in 1993, where it says, "I don't think so." So that's sort of the theme of where we're going tonight. And I indicated biomedical research, it sort of flows it flows more rapidly than the Rudy L. Ruggles Biomedical Research Institute of Western Connecticut Health Network and Health Quest Consortia. Catchy as that is. So I thought, look at biomedical. And that alone, that's what we are, and it sounds like it fits together. But as John Murphy was saying, it fits together less often institutionally and intellectually than the need would suggest, because there really are, I think, two cultures: the researcher who wonders how things work and why, and the medical profession, which looks at how to take what's known and to apply that to patient care. And so I was thinking, seems like a good analogy, the forest ranger whose job is to become vigilant in spotting an outbreak of a fire, to use the sort of crude tools he has at his disposal: people, shovels, bulldozers, some dynamite, and some chainsaws, and to immediately try and identify the location, contain the fire, and put it out. That's his job. He may be interested in how it started, whether it was a marshmallow roast or a lightning strike or something, but his job is to identify it, deal with it, and put it out. And the larger the circumference is, or the radius is, the bigger the things he has to pull in to work on it. Planes with flame retardant and so forth. But his job is to try and put it out. And he's not unlike the oncologist who is presented with a patient who has cancer, tries to identify as well as possible what that cancer is like the forest ranger. He's not wondering how it is that a particular cell that appeared healthy went haywire and became a cancer cell. He's got the patient with cancer. And he, like the forest ranger, has some crude tools, even in this day. Oncologic cancer, a cocktail of cisplatin and Taxol, been around for a while, used. Taxol, by the way, are going to be a few wonders of nature I'll mention along the way. This open mic Wednesday here, we can talk about anything, I guess. But Taxol, in case this sort of first wonder of nature point, Taxol is found derived from the the bark of a Texas pine, which grows only in a little bit of California. Now, for heaven's sakes, come on. That's true. There are a lot of wonders of nature that are being unearthed here and elsewhere. So you have a hospital that has associated with it a research institute who scientists do research and physicians practice medicine. I was quipping before because I'll be talking about scientists and doctors. And when I'm talking about scientists, I'll have a lab coat with opens in the front. When I'm talking about doctors, I'll have one that opens in the back. So even if you go get your heart checked, it opens in the back. I don't know. But there really are, in a sense, C.P. Snow wrote about the two cultures of science and humanities. A thin book, but very impressive because they each have different ways of looking at the world, which is not the way they look at it. It's a continuum, and the past, the history since Pythagoras, man has seen himself as the center of things. When Copernicus came along and figured out that the Earth goes around the sun, not the other way around, and then Galileo followed up. Initially, the church was a little disturbed at Copernicus, but he went and died, so that wasn't a big problem. Thought he'd hoped the idea would go away. Then Galileo comes up, and in 1623 he publishes something called the Dialogo, dialogue between three characters, one of them representing Aristotle, who feels that logic is the basis. Like obviously a big lead ball falls faster than a little lead ball. So that was, and the next one was Galileo representing himself, and the third Galileo called Simplicio, which means simpleton, for the church's position. And with the Inquisition reestablished, that was not a wise political move. And he was brought before the Inquisition, and they said, you have to stop saying things like that. You promise not to do that again. And you know what goes on in the basement if you don't, of the Inquisition. So he said, I promise, I won't say that. He was banished. He couldn't write, read. I mean, he couldn't talk to anybody. And so after this kerfuffle, when the Earth was shown indeed to go around the sun, everybody woke up the next morning and felt pretty much the same, and things went on. The word science that we use so freely wasn't actually coined until the 1830s by a professor at Cambridge. And up until then, science has been called natural philosophy. So it never quite got over the hump of being lumped within philosophy, and it had been an empirical science for a long period of time. But since that time, science has grown in its own image requirements, expectations, discipline, and so has medicine. But I think there's some contrasts that are, I think, important. When I talk about, and John talked about bringing the Research Institute into a patient-oriented environment, and that is that, as I said, the scientists are looking at what and how. What caused that cell to become cancerous when it appeared like other cells that weren't, and how will it change into something that can be dealt with? The doctor, as I say, takes the patient and tries to cure them. The doctors, the Hippocratic Oath says, do no harm. And what that really is saying, broaden your scope, your capabilities, your knowledge, and spend a career healing, but no oopses, along the way, which would please both your patients and insurance companies. But a life lived around not making mistakes doesn't invite the most experimentation or risk. And of course, many doctors do take those risks. And the nature of a risk is it's risky. Scientists live in a whole world of oopses. That's their business, is oopses. And they're looking for an occasional aha out of all of it. So those two, they have different orientations, different reward systems, and they grow up with different different expectations and even measures. Scientists are measured on the outcome of their work, their creativity, the number of ahas they can get out of their work, and the doctors and hospitals are judged on outcome. How's it work out? How many patients have you cured? Which is a laudable and necessary. You don't go to the doctor who knows the most about what you have. You know the doctor who knows most about how to cure what you have. So there are two cultures, and we're fortunate here to have outstanding people on both sides and a leadership that understands that it's complementary. And what's particularly good, when I say that we're at really an inflection point, I think, in actually man's whole view of himself at this point. Now that's sort of grand. Is that big enough, Grace, for a sort of campaign slogan? Think small so you can think big. But in the past, really, it's been the case that we've begun to peel layers off of the onion and research and apply that information. But we're cutting through the onion right now and having all the different layers to look at. And well, it was known that the DNA consisted of 4 nucleic acids. It wasn't known how they were assembled until Watson and Crick came along, and they said it's a spiral staircase, double helix, and so they figured out the configuration of it and what it consisted of, and so you now know what it looked like, what it shaped like, a long spiral staircase with 3 billion stairs, it so happens. And I was going to say, and this is, I have 2 pennies here. I'm going to give them to Development Fund after this. If they can, those 4 nucleic acids can only pair 1 and 2 together with 3 and 4. Already that's sort of restrictive. So that put together in combination of 3 billion base pairs is what you're made up. That's the program you come with. When you have that, you don't have a person yet. You have the program for creating a person. And so not only that, but just to give you some whiz-bang numbers, this thread of DNA is about 1/4 of a millionth inch of an inch in diameter. So it's pretty skinny. But if you stretch the darn thing out, remember it's 3 billion, it's 6 feet long and 1/4 of a millionth of an inch in diameter. That's a wower. And then in a cell, but you still don't have anything living when you have this DNA. That's because all of these 1s, 2s, and 3s and 4s have to be in exactly the right order. So 1.5 billion flips won't get you a human. It'll get you DNA, but it isn't a human DNA. And so the sequence in which those nucleic acids are set down, you have to do it just right, so something knows what's just right, so that you can do it. So get your head around that. But it's true. And if there are errors here and there are abnormalities, some of which don't allow the subsequent organism to live, but it does allow for blue eyes, blonde hair, brown eyes, blue hair, whatever. Any combination obviously is evident from, available from that. But as we look ahead, and the scientists are beginning to understand more about the consequences of the program, still the wonder of nature that surrounds this is, the faster we run, the faster the wonders appear, I think. We've been in an era of man being the measure of all things, we felt, not an era of humility, to one in which we will find that I think man is not the measure of all things. It's, I say, an age of humility, starting right about now, when just the example of DNA and how it's put together, there's a blueprint for putting it together so that it turns out to be our 3 billion base pairs. We all have different ones, but that's our basis of our life form. Every life form has its own little DNA. And, 3 billion base pairs, that's pretty big. We're pretty big stuff. We walk, we talk, we do other things. Then along comes somebody who finds a little wildflower up on the slopes of a mountain in Japan. Pretty flowers like a dogwood flower, do the DNA sequencing. It has 150 billion base pairs, 50 times ours. So we aren't such big stuff after all. And it's slow growing. Why is it slow growing? Because to replicate, it has to zip apart those much longer strands of DNA and put them together. So jumping ahead, that DNA, which doesn't have any vitality, has a program for creating life, but it isn't live. It's just lying there as a bunch of chemicals in a proper sequence. Jumping ahead, at the point of fertilization, a human cell now has a combination of ingredients from both parents, and it starts immediately, mitosis, dividing into equal pieces, and it starts 2, 4, 8, 16. They're all identical. It goes on that way for a few days, not differentiated. They're all cells, identical cells. At some point, a voice comes over the loudspeaker and says, don't stop what you're doing, but listen up. From the next division on, you're going to have particular tasks. You become part of a liver, you become part of a toenail, you become part of this. And so they start to specialize and go off to do what they're doing. Well, as I refer to them as your cellmates, they each have these challenges. They're heading off to become something special, but there has to be a template of what they're going to be. A liver isn't just a bunch of cells. It's something that performs a function, it has a shape, a form, interaction with things, electrical, other relationships with other organs, with the bacteria that exist in your innards. By the way, you have more bacteria cells on and in your body than your body itself consists of, by about 3 times. You're hosting, as we stand here, as we're hosting you, you're hosting 3 times the number of bacteria on and in your body than your body has. Who's the host? And you have about 2 pounds, believe it or not, of bacteria in your gut. 2 pounds. That's a lot of little bits adding up. And these 2 pounds aren't just working on digestion. They affect the human immune system. They affect all other things. And the populations of the microbiome, the bacteria, are different in all different parts of your body. Even within the mouth, there are half a dozen types of, more than that, types of bacteria underneath your gum, above your gum, back, front, under the, it's unbelievable what's going on in there. So it's a little hard to keep your chin up and say man is the measure of all things. When the undifferentiated cells are told to go off and form a liver, and then the whole thing comes together, not because they know what they're doing, but they're somehow told what they're doing. A living, breathing human comes out of all this because everybody's on the right place, interact with everything else correctly on some blueprint that it's going to take us a long time to figure out. We can see what results from problems with assembly. Doctors help, we have answered one question. That is, which came first, the chicken or the egg? Well, the answer is the chicken is an egg's way of getting other eggs. The job is to continue with the DNA. The chickens come and go, we come and go, but our job is to continue DNA as it is for each living thing, and large and small. And it's not always the same design. If you want to be amused at how the architect played around with how to bring about reproduction, strange as it may seem, check out the kangaroo's reproductive system. It was a one-shot. Why not try this? Stopped with a kangaroo, but it is unique, let me tell you. And so it experiments around, but it tries, at any given time, nature has provided just a tremendous range of living critters so that I was referring to it as, thinking about it as an organization that has the geology department and the life sciences department. The geology department, one of their projects was our solar system. So they're pretty damn good. They took planets, each of which is made of totally different substances, different weights, and put them exactly in orbits, going exactly the speed that if they went faster, they'd go out of space, slower, they'd go into the sun. They stuck those out there. It's like juggling a bowling ball, a ping pong ball, you know. They got that going. They also had put Earth in a band, give the life sciences group a chance to work on something that's not too close to the sun, so it's not too hot to support life, not too far away. The three bears, it was just right. And just to show off a little bit, they put the Earth in a elliptical orbit, spinning on its axis, going around that thing once every year, its own orbit once every 24 hours, tip the axis about 23 degrees, so you get seasons. And then for its final hat trick, stuck a moon up there, so that its one face is always and forever facing us. It's doing all of these gyrations, but, you know, like, see what I can do? Now, you life sciences guys get to work on the Earth part. And the life science department figures it's got its responsibility to be sure that DNA, that life continues as long as the planet does. And the geology department has a planet that is hot, cool, has oceans above us, a mile of ice, and that goes away 10,000 years ago. Earthquakes. So you got to sort of get life that's going to make it through what the geology department presented you with. So you produce lots and lots and lots of living things on these blueprints that we don't know anything definitive about. And you scatter that everywhere. And so whatever they throw at you, something's going to go along. We call it extinction. It was just prudent. If you want life to go on, you produce lots of different kinds, live in lots of different environments. And main thing is to have somebody reach the finish line, whatever that is. And even these things compete for, it gives them little games. Like Sally and I were down in the bottom of the Atlantic Ocean in a deep submersible, Russian, of course, is the one that if you saw Titanic and you saw the Titanic sitting down at 12,000 feet, the first things, that was the one that took the pictures when we were in. And so on the way down, it's pitch dark, black, and there are all these little critters. I've always seen those angler things, fish with a big thing on, like huge. I thought it would like devour the thing. It's about this big, but they never show it with a ruler. But anyway, you see all these things coming down, and there are lots of things that have little phosphorescent glow points on it. And so each of them has their own little pattern, so it can tell when another one is like it, because it's dark, so how are they going to tell? So they have a problem. Being not too intelligent, they still have a problem. If their lights are on, it attracts a mate. It also, you become dinner. So when do you turn your lights on, and when do you turn the lights off? But they persist. So anyway, nature presents a whole range of things, and we mourn the distinctions of the extinction of some of them, but that's part of the game. And all this comes down back again, circles back on medicine. The more we know about the fundamentals of life, that which causes it, the more together, close together, becomes individual patient-oriented medicine. The more you know why that particular person's cells became cancer cells, or that particular person succumbed to an infection while others didn't, that also moves over to the care, because once you know that aspect of diagnosis, which goes beyond what currently exists, knows more about what it is you're diagnosing and how it's particular to that patient. It also is at the same time in a period where, John mentioned nuclear weapons. We don't do nuclear weapons testing anymore. It's first atmospheric, then underground, then nothing. We haven't given up. They're designed as you know, in computers. The whole very complicated, it's not just light a fuse kind of thing. It's very, very complicated. But it's all simulated in a computer and in whatever level of performance there you want to have, but never blowing up. And in the same way as one friend of mine here in the audience knows that you call it designer genes, that you take that medicines are not being not a white powder sprinkled on agar agar and see whether it kills the little culture, but understanding what it is that can bring about both detection and determination of a disease. And the more you know about the disease process, the more it provides guidelines for developing medicines to treat both that particular illness or condition, but to be targeted specifically to individuals, as some of the work here is doing, which patients we know that, say with particular gynecologic cancers, that the treatment you're providing will help 80% of the patients and not 20, but you don't know that on an individual, whether you're in the 80 or the 20. We're learning how to get biomarkers that will indicate whether you're in the 80 or the 20, which is a byproduct. There are a lot of pharmaceutical companies with lots of bottles of stuff on the shelf because only 70% of the people they treated were cured, 30% didn't make it to the market. Now, if you get a biomarker, that you can cure 100% of that 70%. You got a new drug, and you have to know what it is to sort out the biomarkers to sort out who will be affected by it. And I know the some pharmaceutical companies are doing like the nuclear weapons types. They're designing pharmaceuticals based on their knowledge of in-depth knowledge of the individual and what that condition the individual provides, so that it can be tailored to populations, and in some cases maybe even specific individuals. So it is a new world, and one that we're sort of ahead of the pack in bringing together those who are trying to look at the what and the how on the research side, in combination with those who are working on how to apply what we know, not only to treatment generally of patients, but even like ancillary things. I know immunology, if you don't find something that kills it, they're now working on enhancing the immunological component of disease and condition fighting, so they can bring both together, almost guide it to its destination. So I don't think it's understating to say that we're really on the avenue of a new era, but that we are beyond that threshold. So I spoke over the amount I was given, but who can prove that I did, okay? In this uncertain world. So thank you very much for listening. And here are your 2 penny cakes. That's the essence of life, remember? Thanks.